Hey everyone, and welcome. Today, we're diving into a really cool paper that uncovers the hidden geometric rules of life itself. Yeah, you heard that right. It's all about how our tissues build and shape themselves, all the way from a tiny embryo to a whole organism. And it turns out, the secret might be way simpler and more beautiful than we ever thought. So it all boils down to this one massive question. We all start out as, just a little clump of cells. How on earth do we get from that to a person with arms, legs, and organs all in the right place? This incredible process is called morphogenesis. And honestly, it's one of the biggest mysteries in biology. Well, a huge part of the answer is that our tissues can act like a kind of smart fluid. Seriously, cells can actually flow, squeeze past each other, and totally rearrange themselves to build complex shapes, all without the tissue falling apart. We see this happening all over the place, and something as delicate as a fruit fly's wing or in the early stages of a zebrafish. So to really get how this works, here's our game plan. First, we're going to look at what I'm calling the cellular square dance, how cells swap places. Then we'll get into the pure geometry behind that move. We'll find out what makes it easier or harder. And finally, we'll talk about why any of this really matters. Okay, so how do cells actually move around when they're packed together so tightly? Well, it all comes down to one single fundamental move. And that move is called a T1 transition. This is the absolute core mechanism that lets tissues flow and sculpt themselves. You can really think of it like two partners on a crowded dance floor gracefully switching neighbors. And this little dance has three simple steps. First, you've got two cells sharing a horizontal side. Then that side shrinks down to nothing until they just meet at a single point. And finally, a new edge grows, but this time it's vertical. The old neighbors have separated and new ones are connected. That simple swap, that's the key to everything. But, and this is a big but, this swap isn't exactly easy. For cells to change partners like that, they've got to overcome a pretty big challenge. The paper puts it perfectly. They have to climb an invisible hill. So what is this hill? Well, physicists call it an energy barrier. It's basically the energy cost of getting through that tricky middle step where four cells all meet at one point. The higher that hill is, the harder it is for the swap to happen and the more solid the tissue acts. So what decides how high this hill is? You'd probably think it's all about super complex biology and proteins, right? But the brilliant insight in this paper is that the answer is actually pure, simple geometry. Here's the core idea. The energy it takes for two cells to swap places is almost entirely decided by the geometric shape of their four surrounding neighbors. These outer cells basically create a frame, and the shape of that frame is everything. These four cells form a quadrilateral, a four-sided shape. And the research shows you can figure out the entire energy barrier just by knowing two things about that shape: the lengths of its two diagonals and the angle where they cross. That's it. It's a beautifully simple solution to a complex problem. Okay, so now that we have this powerful geometric tool, we can start asking some really interesting questions, like what kinds of cell arrangements make it easier for them to swap places, and which ones make it way harder. Let's check out what they found. First thing to know is that real tissues are not these perfect, neat honeycombs. On the left, you see the ideal version, where every cell is a perfect hexagon. But on the right, well, that's what real life looks like. It's what that fruit fly wing actually looks like: a messy, disordered bunch of cells with all different shapes and sizes. So this brings us to our first big question. Your gut instinct might tell you that a messy, jumbled up arrangement would make it harder for cells to move around. So does all this geometric disorder help or hinder the cellular square dance? And here is the first big surprise from the paper. It's totally counterintuitive. But that geometric disorder, that messiness, actually lowers the energy barrier. It makes the invisible hills smaller and way easier to climb. So, a less perfect tissue is actually a more fluid tissue. But hold on, there's another piece to this puzzle. Real cells aren't just static. The forces, or tensions, that hold them together are constantly jiggling and changing. They're fluctuating. So what effect do these noisy, unsteady forces have on that T1 transition? And here's another fascinating twist. While a random jiggle might just happen to give a cell the little push it needs to get over the hill, the paper's math shows that, on average, all those fluctuations actually increase the energy barrier. They make the tissue more resistant to flowing. Okay, one last scenario the paper looked at. What if the forces holding the cells together are nonlinear? The best way to think about this is like a rubber band that gets insanely tough to pull the more you stretch it. That resistance just skyrockets. Well, the result here is pretty dramatic. These nonlinear forces basically make the energy hill incredibly steep. They put up a huge fight against the T1 transition, practically locking the cells in place and making the whole tissue much more solid and rigid. All right, so we've got these three key findings about disorder, fluctuations, and forces. Let's zoom back out now and talk about the big picture here. Why does any of this, the geometry of a single cell swap, actually matter? So let's just recap real quick. 1. Messiness is actually good for flow. It helps cells rearrange. 2. Those noisy, jiggling forces, on average, actually make tissues more rigid. And 3. Certain types of forces can act like a powerful brake, almost completely stopping cells from swapping places. So why is this such a big deal? Well, this geometric insight lets scientists build way more accurate computer simulations of how we grow. It helps explain these critical moments in development, like when a part of an embryo needs to suddenly switch from acting like a solid to acting like a fluid. At the end of the day, it gives us a brand new, more elegant set of rules for the physics of life itself. And that kind of leaves us with a final, mind-bending thought. The incredible complexity of how an organism is built might actually be governed by principles as simple and timeless as geometry. And if that's true for the dance of ourselves, what other profound secrets about how life works are hiding right there in front of us, just waiting for us to look at them in a new way?